Hello and welcome back to this series about computer networks and specifically the third layer. In the previous video, we understood why we need logical addresses in addition to physical addresses. In this video, we'll start learning about IP, the Internet Protocol, which is the most commonly used network layer protocol on the Internet. In the current video, we'll focus on IP addresses, specifically in IP version 4, IPv4. IP addresses are hierarchical, logical addresses. Each consists of 4 bytes or 32 bits. We usually write them in dotted decimal notation. For example, 12.4.98.6. So, does the following address represent a valid IPv4 address? Well, no, it doesn't. Since the dot separate between bytes, each value will be between 0 and 255 inclusive. Since the number 392 is bigger than 255, it cannot be represented in a single byte. IP addresses have in fact two parts: a network identifier that belongs to all hosts in the network, and a host identifier, which, as its name suggests, identifies the specific host in this network. The network ID will be the same for all hosts in the network and is also called a prefix. For example, consider a network identifier of 201.22.9. Given that this is the network prefix, we can tell that the following addresses are part of this network, and they share the same prefix. The first address belongs to host number 15 in this network, and the second belongs to host number 91. This address has a different prefix or a different network ID, and thus belongs to a different network. In this example, we had a network identifier consisting of 3 bytes or 24 bits, and a host identifier consisting of a single byte or 8 bits. A question arises then: how do we know which bits are part of the network ID and which are part of the host ID? Well, let us consider the following solution. Say that for every IP address, the first, most significant byte would be the network ID, and the remaining 3 least significant bytes would represent the host ID. This way, it is really easy to read IP addresses. For example, for this address, we know that it describes network 20 and the host 12.192 inside that network with the identifier 20. Any IP address that doesn't start with 20, such as this one, would reside in a different network, and any IP address that starts with 20, such as this one, would be within the same network. Well, what are the disadvantages here? So we only have 1 byte or 8 bits to represent our network ID. That means we only have 2 to the 8th power, or 256 different networks. Obviously, we have way more networks than that in the real world. So, in general, using a fixed length for the host ID is just not flexible enough. If we decide that the 2 most significant bytes will represent the network ID and the 2 least significant bytes will represent the host ID, then we can represent out to 2 to the 16th power, or 65,536 networks, which is, well, also not enough. Furthermore, some networks, such as those of really large companies, might require more than 65,536 host IDs. The solution lies in providing some flexibility. Let us consider another approach called Classful addressing. In this approach, the number of bits dedicated for the network ID changes from one address to another, and we can tell the network ID when we look at the first most significant byte of the address. Any address starting with a number between 1 and 127 belongs to class A, meaning that its network ID consists of 1 byte, leaving 3 bytes for the host ID. Any address starting with a number between 128 and 191 belongs to class B, which means that its network ID is 2 bytes long and its host ID is also 2 bytes long. Any address starting with a number between 192 and 223 belongs to class C, so it has 3 bytes of a network ID and 1 byte of a host ID. I will shortly mention the other values for the first byte later, but just to make sure we understand this approach, what class does this address belong? Try to answer for yourselves. So since it starts with 130, which is between 128 and 191, it belongs to class B. This means that its network ID is 130.12 and its host ID is 204.5. Let's mark it as address number 1. Do this address and address number 2 belong to the same network? Well, no, since they have different network identifiers, they are not within the same network. What class does the following address belong to? Correct, it belongs to class C, as the value of its first byte, 200, is between 192 and 223. This means that its network identifier is its first 3 bytes, 200, 1, 1. And any address starting with this prefix will reside within the same network, and any address that doesn't start with this prefix will not reside within the network. This specific address describes host 9 within this network. Just to complete the picture, let us quickly describe the remaining values for the first byte. So addresses starting with a value between 224 and 239 belong to class T, which represents multicast addresses. These are addresses that belong to multiple devices, as we described when talking about the Ethernet protocol and Ethernet addresses in the second data link layer. Addresses starting with a value between 240 and 255 are reserved for future use. Addresses starting with 0 are special, and we'll discuss them in the video addressing special addresses. No pun intended. So, classful addressing allows for more flexibility compared to the previous fixed length approach we've described. Yet, even this approach is just not flexible enough. Consider the following scenario. I'm starting a small startup company with 2 friends. We need to get a network identifier for our network. Well, which class would we need? So getting class A or class B would be way too much. So we can get a class C that is allowing us 256 addresses. This is more than we currently need, but it will allow us to expand in the future. Let's assume that my startup company is being successful, of course, and we grow and hire more employees. We get 100 of them, maybe 200. And then one day we have more than 256 employees, meaning we need more than 256 addresses. Taking 256 for simplicity, that's without counting addresses for other devices such as printers, network devices that require IP addresses, and so on. At this point, what kind of address do I need to get since I want all the devices in my company's network to share the same network ID? Well, I need to get a class B address, giving me no less than 65,536 addresses, when all I need is just a bit over 256 addresses. This means a waste of more than 60,000 addresses. This could have been a purely theoretical issue, but soon enough, even in the early 1990s, a real problem emerged, a real outage of IPv4 addresses. As the internet grew really fast, faster than anyone anticipated, the need for more IP addresses became apparent, and there were actually no more addresses to allocate. This kind of case where 60,000 addresses are just wasted was no longer bearable. This issue of not having enough IPv4 addresses is a really important issue in computer networks, and we'll continue our discussion of it in future videos as well. One of the measures, and only one of the measures, to handle this outage was to abandon classful addressing in 1993 and switch to another approach called CIDR, which stands for Classless interdomain routing. This approach is still in use today. CIDR allows for flexibility when choosing the network ID and the host ID. Let us consider the following example. This slash notation is the convention used to specify how many bits describe the network ID. So in this case, 16 bits describe the network ID. That is the 16 most significant bits. In this case, these are 200.8. So 200.8 is the network identifier and 3.1 is the host identifier. Consider addresses 5 and 6. Given this address prefix of 16 bits or 2 bytes, which of these addresses belong to the same network as address 4. Address 5 does not belong to this network, as its first 16 bits, 200.2, are different from the first 16 bits of address number 4. Address 6, however, does belong to the same network as that of address 4. Another way to express the network prefix is by using a subnet mask, like so. When converted to binary base, 255 in decimal means 8 times 1, or 8 ones. So all bits in this byte are on. So if we translate this mask into binary, we get 16 consecutive ones followed by 16 consecutive zeros. In other words, 16 are on, which means the network prefix of 16 bits. Both conventions are used very frequently, both using the slash notation as well as using subnet masks. Notice that with CIDR, an address can reside in different networks, given different network prefixes or subnet masks. This is different than classful addressing, where when you know the address, you also know what network identifier it has. If we consider the same address 4 with a different prefix, say that of 8 bits, what would happen now? So now both address 5 and address 6 belong to the same network as address 4, as they all have the same first 8 bits, the byte 200. How will we represent the network prefix of 8 bits as a subnet mask? Well, we need the first 8 bits to be on, so that means 255 in decimal, and the remaining bits are off, so we get this subnet mask. What happens if we use a network prefix of 24 bits? Well, first, how would we express that as a subnet mask? We need 24 bits to be on, 3 times 8 bits to be on, so we'd get 3 times 255, followed by a 0. Now, neither address 5 nor address 6 reside within the same network as address 4, since they don't share its network ID, that is 200.8.3. Note that network prefixes do not have to represent full bytes. For example, we can use a network prefix of 12 bits, or 11 bits, or 22 bits. We'll practice these on the next video. In this video, I just wanted to focus on the different approaches to selecting addresses in IPv4. Note that this fact addresses the issue we've considered regarding the startup company. If my startup has 300 employees, then I need to get a 23-bit network ID, leaving me with 9 bits for hosts within my network. This means 2 to the 9th power, or 512 addresses, which should be enough, and significantly less waste compared to 2 to the 16th power, as we described earlier. When in this video we talked about IPv4 addresses, we said that IP addresses are hierarchical logical addresses that consist of 4 bytes. We mentioned that IP addresses have 2 parts, a network identifier that belongs to all hosts in the network, and a host identifier, which identifies a specific host in the network. We considered various options for determining the network identifier and a host identifier. We first mentioned the fixed length approach and then the classful addressing approach. As both were not flexible enough, we moved on to consider CIDR, where an IP address is joined by a network prefix. This allows a lot more flexibility and helps us overcome the great problem of shortage of IPv4 addresses. As I've mentioned, CIDR is only one part in overcoming the shortage of IPv4 addresses. We will deal with this issue in future videos as well. In the next video, we'll practice the concept of CIDR and make sure that you understand it well and that you feel comfortable with it. I'll provide you with different network prefixes and ask you to convert them to subnet mask, and vice versa. I will also ask you to determine whether 2 addresses reside within the same network, given different network prefixes. After we feel confident enough about CIDR, we'll discuss special IP addresses and then start investigating the header of IP packets. I hope you're as excited as I am, and I'll see you all in the next video.